Okay, hello everyone. Welcome to the IDS seminar. Today we are very honored to have Professor Daibo from IDS to give us a talk. His talk focuses on how to generate interactive and physically plausible 3D indoor environments for simulation and embodied AI. He presents two complementary approaches, a top-down method using language models to plan scene layouts, and a bottom-up method that learns object relationships to build scenes step by step. And the work highlights how combining semantic reasoning with spatial structure can enable more realistic and usable 3D environments. So let's welcome Professor Dai.
Thanks for the introduction, and thank you for coming this seminar, especially today. Tomorrow is like vacation. And yeah, today's topic is about how to close this one. Yeah, anyway, today's topic is about 3D indoor scene generation. And like this topic is related to the several hot topics in AI, like embodied AI, world model, and also agents. And yeah, can we remove this one? Okay, thank you. Yeah, so like for embodied AI, you know, like if you want to train like those good policies, one way is to use simulation environment and to train them in this virtual environment, then adapt them to the real robots. But you see, like in this like modern simulation platforms like Isaac Gym, Isaac Lab, and the new one like Newton, you know, like still the environment are not that realistic, like kind of like random and randomly generated, so kind of like limited the upper bound of trained policies. So if we can generate like more realistic 3D environment, then we can embed deploy those environment into the simulation platform and train like more powerful like policies. And also for like world models, like everybody, it seems like everybody are talking about world models right now, and there are like a lot of like different like pipelines. One pipeline is to build a 3D like realistic environment, and possible ways to like using 3D Gaussian splatting. And this is an example a work from the World Lab, led by the Professor Li Feifei. And using this method, you can generate like a 3D environment that supports like free traversal in this environment from a single image. But the whole environment is like a whole, like cannot be separated, and the assets in this environment cannot be like moved or not that interactable. So that's why like we want to build like a 3D environment that can support like more complex interactions. Like you can move the chair from one place to another place, something like that. And finally, about like autonomous agents, you know, like OpenClaw and agentic AI have like advanced remarkably, and this is the work like generative agents and. Until right now, like the agentic AI, those autonomous agents can only like people usually use like 2D image or like a text-based environments to test and develop autonomous agents. But if we can build like 3D interactable things, we can like further enhance the capability of autonomous agents. So that's kind of like the importance and the reason why we study 3D scene generation, because it's kind of closely related to both embodied AI, old model, and also autonomous agents. Okay, and like the task definition of 3D indoor scene generation is like we want to build like a 3D scene with separated assets, like each asset in this scene is like an isolated entity, so you can move the entity from one place to another place, and the different assets can have different functionalities. Okay, and the input condition can be an image or a text prompt or any other like condition signals. But because like today we will not talk about like how to handle different condition signals, but focus on how do you make the whole generation process more like efficient and controllable. And yeah, and usually like methods in this area can dealing with two subtasks. One is to finding a suitable like layout, like configuration that tell the machine like the place and the material attributes of different asset. And the second subtask is like to actually generate or retrieve this 3D asset. And you know, like because like the progress of 3D asset generation or object generation is like very good. So usually in the task of 3D indoor scene generation, people focus more on how to generate like plausible and complex layout, and using like retrieval or off-the-shelf 3D asset generation method to get the asset themselves. So so that's why the works I introduced today is also focused on how to generate layout using different approaches. Okay. And the challenges of layout generation is like the first one is the complexity of layout. Like a scene can contain many objects, and this kind of like, and also like physical constraints. This kind of like make the whole solution space very, very large. And the second challenge is the data scarcity, because I think we all know like 3D data is already significantly fewer than like the amount of like available images and videos. Like in 3D data, like 3D assets, the amount of like single objects is like significantly richer than the amount of like available 3D scenes. So 3D scene data is extremely limited, and so that hindering the large-scale model training in this task. Okay. And this is a concrete example of the available data sets in this direction. So usually people use 3D front or ScanNet to train models. And the 3D front is a synthetic data set, contains only like several like thousands of rooms, and the ScanNet is like a real-world dataset. Like people use scanners to scan different rooms, and in total, this dataset only contains like less than 2,000 scans. So the comparison is like for image dataset, like the famous Lion 5B, like it's a dataset containing like 5 billions of image text pairs. So this kind of like the comparison is like pretty like clear. So 3D scene data is really like scarce. So that's kind of like enforce us to think like a clever design or pipeline to generate the layout. And the choice and like as we just said, like the in 3D scene generation, we focus on how to generate like plausible and the complex layout. And the key of this subtask is to find a good layout representation, so that it defines the search space and also like the inductive bias we can use, and this will affect the capacity or the expressivity of the method, like how complex the generated layout can be, and also it will affect the efficiency of the generated method, and also the editability. Like can we like how easy can we to adjust the generated layout? So this kind of like capacity properties are all strongly related to the choice of layout representation. And today we want to talk about like our two exploration towards this answering this question. Like each paper is like discussing the one possibility of the layout representation, and the first one is like a top-down approach, and the second one is a bottom-up approach. And both of these two works are the major contributor is my student Ran Xinjie. Yeah. Yeah, we're going to go through these papers one by one. So the first paper is called Direct Numerical Layout Generation for 3D Indoor Scene Synthesis. And in this work, we define the format of 3D layout to be the set of like objects, the attributes of objects. So the layout is consisting of like the attributes of different assets, and the attributes include their locations and their size and their like orientation, and also the attributes. So so in this way, like the 3D scene in the left can be represented using the corresponding representation shown in the right part. So it contains like different like bounding box, or kind of like define the size of the of each asset, and also like the corresponding text description, kind of like describe the details, the semantic details of each asset. So in this way, we can we kind of like find the representation of the scene layout, and we further inspired by the after we have this one, we kind of like trying to answer how can we design a model that can like effectively generate such a representation. So our like solution is like we can further represent this this set of like assets to like a domain-specific language, or we represent them using using code. Like we represent this information using like a JSON file, so that it forms like a domain-specific language. And the benefit of to represent layout as code or program is that we can then utilize those strong pre-trained language models, because they're like they have strong capability, and the people put a lot of effort to advance its coding capability. So this is a figure like say the development, the advancement of language models in terms of its coding capability. You see like they are becoming stronger and stronger. I think like most of you have like using them to facilitate your coding tasks. So you can already like feel its like coding capability. So by representing the 3D layout as like a domain-specific code, we can then use this borrow this capability to solve the problem of layout generation. Okay. So so the training, the overview of the training is shown in this page. So the process is kind of like straightforward. You just collect the data, collect a bunch of like data, and then you use like supervised fine tuning to tune like open sourced language model, and in this way, you can then the fine-tuned model can then generate like different layout in the form of like JSON code. But this, if you examine like in detail, you see like for data collection, we explicitly collect like the process data, like the chain of thought process, and use them to during the like supervised fine-tuning. So the reason is because like layout is kind of like a complex code. You have to consider the different relationships between the assets. So if we just ignore the chain of thought without using the chain of thought guidance. We just like collect the final complete JSON code and do the supervised fine tuning. The model will not perform that good because kind of like it will get lost in the middle, like forget about some of the previous context to resulting in like the layouts can have many artifacts or overlapping assets. So we kind of like using the chain of thought process to inject some like human priors. Like we can divide the layout generation process to like we first identify the identities, we then like decide the order, resembling the process like how we decorate a room. Like say we think about what kind of like furniture or assets can be included in this room, then we decide their like placing order, and then we kind of like finding the place of different asset, then we kind of like form the final like answer. So it's kind of like a way to inject human bias in the process, and this can significantly reduce the complexity, learning complexity, and help the language model better adapt to this task. Okay. Yeah, and besides like SFT, you know, people right now for like fine tuning of language models, we can also use like reinforcement learning or direct like preference or optimization. So in fact, in this work, we also did that to improve the generalization ability of the model. So but like as in other similar methods, the key of like conducting DPO or other reinforcement learning strategies to design proper rewards. And so most of the efforts we conducted focus on like how to design different like reward functions to guide the model to generalize to more complex and unseen like room type. Okay. And the rewards can be divided into like object level and scene level. So for object level, we further divide it into like, it's kind of like the constraints or rules you will consider when you try to decorate a room. So including the spatial rules like the relative alignment, like for like a chair and a table should be like placed near each other, and for like the global positioning, like usually like the bed will place in a place like close to the wall, and also like the consistency with the chain of thought process. And also we have besides like those spatial consideration, we also have to when we decorate the room also consider its overall like comfortableness and like the visual quality. So that's why we also use several like qualitative evaluator that to kind of like to measure the overall quality of the layout, including like the distance between different objects. So if like all the assets are like placed near each other, the whole room will look like a mess. And also like the size should be like consistent across different assets, and also the orientation validity, like the orientation of the bed, like usually have like some empirical preference, something like that. So you see like different rules kind of like trying to measure a fact that related to the overall quality of the layout. And these are the object level like rewards we use during the direct preference optimization process. And another thing we need to consider is the scene level. Is because like unlike like you do, I say, for example, like image or video generation tasks, usually the resolution are fixed during the training. So all the image looks like the same size and the same complexity, but that's not the case in layout generation. So you see like there are like rooms, like simple rooms that contains only like 5 to 4 assets, and there are also rooms like classroom or the meeting rooms that can contain like tens of assets. So the complexity of those layouts are different. So if we treat those layouts equally, the model may like collapse and learn towards like those simple cases. So that's why at the scene level we also adapt like a reweighting scheme to try to balance the contribution of different layouts. So so the overall is kind of like we compute the entropy of different layout. The entropy is computed by like given the same input condition, we generate like k copies or k instance of this condition. We then compute the t instance, and then we use this t instance, we try to compute the entropy, and then we use this entropy to reweight the contribution of different like layout instances. So in this way we balance the training process so that the model will not like collapse into like only generate like simple cases. Okay. Yeah, so this is the inference process. So at the top is like we go through the process, like we having like the condition, we can then generate the layout, and use this layout we can then apply an object generator or like a retriever to retrieve the asset from a library. Then we assemble this assets into the final scene, and so after we have this final scene, we can further like do some test time like optimization, because like after we have this scene, we can render the images, and we can use this image to reuse those like evaluators to examine the qualities of the scene, not only by just looking at the layout, but looking at the overall like scene to give some feedbacks, like further adjust the locations and the size of different assets to further improve its like quality. So that's why this has like a iterative asset layout alignment to like we conduct several rounds of this test time refinement. We can further improve the quality of the generated scene. Okay. So this is the results, and this work is published last year in like Europe's 2025. So at that time, the SOTA models are these three, and when you can compare like visually from like the results of ours to the results of the baselines. So overall, like our results are like both like complex and natural in terms of its layout, and also like in this like in a scene that have many assets. And I should emphasize this like more like a classroom scene is not seen in the data. So the second row is kind of like representing the like a generalization ability of our method. So, and this is the like the quantitative results, and yeah, and we can see like from these two rows is like we kind of like without like this line is like the result of like just using the supervised fine tuning without using the DPO, and compare these two lines, we can find like DPO can further improve the result. And also these two lines compares like the performance like of like using an open source like model and using like a kind of like closed source API to generate the layouts. From the results, you can see like the performance gain or the performance of our method is not that heavily dependent on the performance of like the underlying like code generation or other like pre-trained models. So it's like it's verified like the performance gain of our model is indeed from from our design. Okay. And yeah, this is like the ablation study, like a qualitative one to show that why we need to consider like inject different like human priors and using different like steps. Like the first one is like if we do not use the chain of thought to inject our human priors to guide the code generation process, the generated layout will be like not that organized. And if we didn't use DPO like to refine the overall quality, we may have some like outliers or artifacts, and like the simple reward can only account for like a certain aspect of the scene. So the results may look like that like good in different aspects. So the full version makes the best results. And I should emphasize like because we at the beginning we said like we want the scene to be like interactable. So the generated scene, like each asset is like an isolated one, so you can move like freely. Okay. And this is like a videos of this qualitative sample, and I cover 3 examples, like from left to right, from like easy to hard. Like the left one is the most like simple thing, and the middle one is like the like a slightly more complex thing, and the right one is the most like complex one. And you can I should say like for the most complex one, you see each bucket is a separate one, so it's kind of like demonstrate the upper bound of this of our approach. But it has like limitations. Although like after we conduct this work and published in like Europe's 2025, there are a lot of follow-ups trying to use like represent layout as code and use like a language model or even like agentic AI to generate layouts. Okay, but in general, in this line of direction, we think there are some like limitations. The first one is like it's indeed rely heavily on the knowledge of pre-trained language models. Okay, and the second limitation is like it has unstable successful rate, because like if you can, it's like the limitation of like using language model and agentic AI, like for like when it succeed, you have like very good result, but you don't have like much control of the how to say, the generation process. Like sometimes it can generate a really bad result. And the third limitation is like the layout complexity is still limited, and it's like limited to the training layouts you have observed, and also limited by the prior knowledge captured by the underlying language model. And the fourth limitation, which I personally believe, I think is like a limitation of like most of work that working on layout generation, is like the generated layout is too formal. It's like you are generating a room that used for like for sale, like placed in the like the demonstrate room in the like those estate vendors. So it's not like the rooms we live, the rooms we live are not that like formal. Like we have like different like assets that just randomly placed because like it's it's like the reason of like those assets being there is not that serious. Maybe just someday we're tired, we just randomly place assets at the on the sofa or on the table, and we keep completely ignore them. So, and this process continues, and as a result, like our living environment are much more like casual and random than the currently the results generated by those by these methods. Okay, so these limitations kind of like lead us to think from another direction. Like in the first work, we're trying to solve this problem in a top-down paradigm. Like we're seeing it kind of like we are the designer, and then after we receive the requirement, we kind of like draw the overall layout, and then according to the layout, we generate asset or retrieve asset, then we assemble the room. But in the second work, our recent work called pair to scene, we kind of like think in the like opposite direction, like in a bottom-up approach, mimicking like how we like how we construct a room day by day after like a long period. It's like you can imagine like the rooms we have so far is like a long process of like every day we may add some new items, and because different reasons we place them at different places, and this process accumulates until we have like complex room. So we want to follow this kind of like a more natural process to generate those 3D things. And the formal reason is like this is like statistics we calculated to like this is the type of assets appears in the data set. So you see naturally it's a long tail. Like say for every room you must have like a table or chair or bed, but like for those items like a guitar or like a lamp, is like the frequency of these assets are not that high. So naturally the distribution of all possible assets form a very like a long tail distribution. And if we stick to the top-down pipeline, we cannot escape from this long tail distribution. Okay, so the model will learn this long tail distribution, and they will put a lot of efforts trying to optimize the location and the orientation and attributes of these like common assets, and they have little chances to optimize the assets that lie in the tail part of the distribution. And this is one reason. And the second reason is like, as we just discussed, like how we form a room in our daily life, the overall layout of a 3D thing is actually formed under various factors, and some of them are redundant to model. Like say, if we follow the top-down approach, we may trying to like remember, like say there's a pillow on the sofa in many cases in the training data set, but in fact this kind of like is kind of just a correlation, not like a depending or causal relationship. So we should, in fact, we shouldn't let model to model this dependency. So and we just said like, for example, if we have like 10 assets in the room, is the possible combinations of these 10 assets are like the space, the number of possible combinations are huge. But if we just like directly model this possibility, we'll need a model with large capacity to do that. But in fact, many of these combinations, it's not smart to directly model this combination in the joint space. We should like find a subspace to model them is much more efficient. So this kind of like those reasons kind of like serve the motivation of why we want to find a bottom-up approach. And this is an example, like say when we decorate the room, when we construct the room, we place assets one by one, and the assets placed into this room because of different reasons. Like maybe just because today I buy an asset and I don't know where to put it, so I find like I just like a quick thought and find a place to put it, and I just put it, and the dependence is not that serious. Okay. So that's why in this work, in our more recent approach, we conduct layout generation to inspired by the procedure generation process, like mimicking like the natural process of. Okay. Anyway, so procedure generation is kind of like a common approach in like game development. Like you have limited asset, and you if you want to have like a complex environment, one way is define the procedure rule. Then you can apply this procedure rule recursively, so that you can generate a very complex environment using simple like or limited assets. And so that's like our attempt in this work. Okay. Okay. Yeah. So you see, like, so it's anyway, like it's divided into two steps. Like if you assume we already have those rules, we can then find a way to apply those rules recursively. It's like, in other words, it's kind of like we add those assets one by one according to different rules. And the second task is like how to extract those rules automatically from the training set. Okay. Okay, then let's continue. Yeah, so as we just said, like, so if we using the procedure generation pipeline, we can then we need to answer two questions. One question is like, assume we already have those rules, how we apply those rules recursively. And second question is like how we learn these rules automatically from data. So in the first question, like say how we apply these rules, the best way to achieve that is like to mimic how people do that. So we use like those language model or agents to do that, like because like in humans, it's like we just randomly pick one like valid rules and we just apply them. So this is like the process. Like we use language model, we can then generate like a order, like the sequence of rules, like the chosen rules, and then we apply these rules. The more like challenging and important part is to answer the second question, is like how we represent and learn the rules. So that's why we will like discuss a little bit more detail in answering this question. So for rules in the layout generation, we consider like we restrict our definition into like owning the capture the relationship between two or three assets, considering only two relationships. One is the support relationship, like a computer is placed on top of a table, and so as the mouse, and also like a lamp is usually placed on like also on the on table. And then the second type of relationship we will consider is the functional relationship, like usually the mouse is placed near the computer, and vice versa, something like that. So we restrict our definition to these two types of relationships, because in this way we can remove a lot of like redundant dependencies we previously needs to model in the training data set. Like if we have a table, and the table there are like 5 assets on the table. It's kind of like having like overturn like possible like inter-object like relationship between a pair of these 5 objects. But in fact, most of these relationships are dependent. They are just happen to placed simultaneously on the table. Only some of the relationships are useful, like because of like the functionality relationship between like those objects. So anyway, so at the end we define the rules to be like we have a dependent object, and we have like a support object, and we have like a function object. So this triplet consists of one possible rules we can use, and the realization of the rule is like given the information of the supporting object and the anchoring object, what is the possible like location and like the size of the third object we want to place. It's like if we already have the table and we already have like a computer on the table, what is the possible location and the size of the mouse? So it's kind of like the centered, it's a distribution centered at the computer. So kind of like model this distribution, and this is the model. So the input is like the like the orientation and the size of the anchor objects, and also the point cloud to reflect this geometry. And after that, we can like using like a transformer structure, and the output is like a mixture of Gaussians to model the spatial distribution of the like the third asset, and like that's and so in during inference, after we learn the rules, how we apply them is like very natural to how human do that. After we like, for example, after we see a table and we see like a computer on the table, we want to decide the location of the mouse. We naturally like will place around the computer because of its like function dependency. And how we actually do that is like among all the possible locations, we will choose one, and we will like think whether we can actually put it. If it not, we then reject this sample and then choose another place. So that's why during inference, we will do the like rejection sampling to find like the actual place to put the third asset. So because of the rejection sampling, we don't have to like learn the like those complex distribution for the rules because of those reasons. Because like the tables, the shape of the table are different, we can ignore those factors in the like the rule learning process, so to make it like as simple as possible, so that we can find the most common information across different samples in the training set. So, and this is like and also because of like this bottom-up pipeline for the training, we can like collect those data more easily from like the existing data set. So for a data set, like for a single thing consisting of like 10 or 20 assets, actually we can collect or extract many like pairs, useful pairs from this sample. And like the process is straightforward. We just identify the semantics of different assets. We then use like off-shelf language model to decide whether they have like a functional relationship or like a support relationship. If so, we then like further extract their attributes information to form a data sample. Okay, and from this process, you can immediately find the thing is like the whole data curation pipeline does not rely on any assumption of like the specific data set distribution. So in other words, like this process, like the whole bottom-up pipeline, make this straightforward and feasible to combine different like different things, like different things like from like data from different sources. Okay, and yeah, because like the benefits of this bottom-up approach is like we can then naturally combine data from different sources, because what we captured is like, what if we have already have these assets, and what is the best location to place a new one, and this information is like consistent, natural in different data sets. It's not depending on a specific data set. So that's why we can combine data from different sources and improve the results. So like from the left is like the results. We train the model on only use data from the 3D front data set. So you see like the overall the 3D front is like relatively simple. So that's why the generated layout and the corresponding scenes are not that complex. But after we like combine the data from different sources, we can create much more like complex scenes. Okay. And another benefit of this bottom-up approach is that we can exceed the complexity of the training set in terms of the layout complexity. because like there's no more like overall like estimation of the layout. You just apply in the rules recursively. So this is like even like we only train the model on the 3D front dataset, only on the 3D front dataset. Like this, the left one is like we strictly assume the number of assets should not exist the maximum number of assets we observe in the training set, so resulting on like a similar complexity of the things we observe in the data. But we can remove this restriction, and there's no like hard constraint on the how many times we can recursively apply in the rules. So if we remove the constraints, we can get much more like complex things from even we only trained on like a single data set. In fact, like this is like a results overall like a result. Like we just compare we just calculated the average number of assets for in the like generated things, and we report this number including ours and also the baselines and also the ground truth, like the blue colors are like the averaged number of assets in the generated things for like 3 different baselines, and the green color is the average number of assets in the data set. So it's like kind of like the ground truth, and the orange color is the average number of assets in our generated things. So you see, like because of this bottom-up approach, we can easily surpass even the so-called ground truth number of objects, even to its like 2 times of its value. So that kind of like reflecting the potential and the upper bound of this bottom-up approach. And also because of the bottom-up approach is divided like the whole generation into like a local, more local generation, more like a more local generation pipeline. So the overall like inference time, so the method is more efficient because it only accounts for the necessary dependencies and the like computations needed to generate the layout. So this is like, that's why the overall running time is like very few compared to like those methods trying to generate the whole layout in a single like forward pass. And also like for the effectiveness, because like still like because we do it like locally, all we need to care is like the constraints we need to care about when we do like a single application of the procedure rule. Okay, so we don't have to like take care of those like physical constraint and other like constraint in a like global sense, which contains a lot of like unnecessary computation. Yeah, this is like the effectiveness, like this is the collision rate, like because we like do it locally, we can put a lot of focus on like those constraints. So at the end, the overall collision rate is really low compared to like baselines that consider the like layout generation in the like top-down approaches. And similarly, in the ablation studies show similar like trend. Okay. And this is like also like a user study, because like we believe like this bottom-up approach is more natural in the like human's perspective, and also like mimicking like how human affect or construct a room. So that's why in the user study, like the overall like the quality more favored, like our generated things more favored by the like humans. Okay. Yeah, this is like the qualitative samples, and also again, like every asset is like isolated, so it's free to like interact with these items. Yeah. So yeah. So we are still working the process because like we didn't talk about like how we inject different conditional signals and like to support like in the middle like edit of these things and but here we can like summarize the challenges ahead. Like we still need to handle. It's like the first one is like we like related to the limitation. I emphasize like still currently the generated things are too formal. So we want to move beyond like those formal and like a role. Like a role model like examples, we need to models that can handle like specific and fine-grained requests, such as like a room for a 5-year-old who loves dinosaurs and has a lot of Legos. We want to do that, make the rooms more like vivid and like casual. And the second challenge is like we'll have mastered like the living room, like a single room, and like a indoor thing. How we extend this idea to like a shopping mall, like a hospital, or like a entire like a city block. And the third challenge we like need to care about is like. Right now, it's like we generate the thing and we conduct like a post-processing process to improve its physical plausibility, and we really want like to bake the physics directly into the generation process, and we believe this bottom-up approach has the potential to do that, and. In the end, because of like the need in embodied AI and world model and also like autonomous agents, we believe like in the generated things, the objects shouldn't just look right; they should also like act right. So it's like because of like the common need in the downstream applications. Yeah. So yes, yeah. So sorry for like the interrupting during the middle, and thanks for listening. Yeah.
Okay, thank you, Professor Dai, thank Professor Dai for the insightful talk. Any questions from the audience?
Thank you, Professor. Thank you for your sharing. I have a question about. So actually, in the first research and second research, based on like the how to say it? So the first research which you encoded like the attributes or let's say the characters into the LLM prompts to help you to generate the 3D layout. So, but in the different scenarios such as hospitals or living rooms, different objects may focus on different attributes. Yeah. So how do we decide in which scenarios which attributes are more important than other attributes? And how should encode those attribute relationship into the prompts?
Yeah. Like as I just said, like right now we like hold more belief in the second bottom-up approach. So to answer your question, the best way we think is like to improve the rules, definition of rules, to improve like to extend the scope and definition of the local rules. Like say you can add like the conditions into rules. Like say if this rule is applied in a hospital or in like a shopping mall, how the attributes will the distribution will change. So it's kind of like still mimicking like how human do that. Like say if you think like you have you want to buy a table and a chair, you will definitely think what is the type of the room, the purpose of this table, and according to that, you kind of have a prior, or this information will change the distribution of possible attributes of the assets.
Yeah, we can use the role base to build the rule tree, and actually it's already used in the second research. You build the tree of the relationship tree for the entities in for the objects.
Maybe I want to clarify. That is like this tree is not like generated in a top-down approach. It's like the result of applying these rules one by one. So it's not like, say, we generate a complex tree and then we follow this tree to generate the thing. It's like we kind of grow in this tree piece by piece. Yeah. I don't know whether this answers your question.
Yeah, but let's say if in the hospital the difference the dental department and the heart department may be different desks will use for different scenarios. So if we try to build this tree in the different departments, I'm not sure whether there is the difference in this application, but I think if there is a tiny difference is how to control the different tree in different departments, but similar, but not so much difference, the tiny difference.
So I still want to clarify. This tree is not generated because you have in different rooms in the hospital. It's growing this tree. So it's see how you decorate. It's you imagine the process of a human decorating the room. It's you have already know the purpose of this room. Then you will think of the assets that may possibly appear in this room. Then there are rules associated with these assets. You will choose one because some reasons. Then you choose one. After you choose one, you will apply this one. So the tree will grow with one more node. So this process continues. So this will the subtle difference you mentioned will naturally reflected in this growing process. Yeah.
Thank you. That's clear.
Any other questions?
Thank you, Professor, for the wonderful talk. So I want to ask, you mentioned about the challenges of the physics-grounded scene generation at the FutureWorks direction. So I wonder, do you have any thoughts about which physical properties should we take in consideration for this generation? How do we evaluate that?
It's there already works towards this direction, important physics factors like the weight of the asset, and also the material of this of the asset, and also the shape, the detailed shape of the asset. Say if the table is contains a slope instead of flat, it's the plane flat. Plane, how you place the computer, something like that. So you just kind of need to add more fine-grained details so that the overall physical possibility is improved. It's you need to replace these point clouds into a more complex representation that can capture richer details of the supporting and also the functionally related assets, so that you can to decide the third object with more information, and also you can further output more information, the exact shapes you needed, or exact weight, or exact material you needed. So it's kind of expanding the scope and the level of complexity of those rules. Yeah.
Yeah, but I wonder, so how will you incorporate the rules into the materials? Because, for example, when you generate the mesh, you can specify the some electromagnetic constants within these mesh properties. So how do you somehow embed the rules inside about the physics here, for example?
Actually, it's an open question. I don't have like an exact answer now, but the philosophy is to find the proper structure and the embedding for the information. So and trying to like leave other things to model to try to make like add a minimal inductive bias, but necessary inductive bias to the model. Then let the model to learn in a data-driven way. That's how we will solve this problem. Yeah.
Okay. Thank you very much.
Okay, so we can leave more further questions to after the seminar. And let's thank Professor Dai again for the great talk.
Thank you.